In this video, I'm going to show you a trick to solving this MIT Integration B question. This appeared in the 2025 semi-final. So in this integral, we are going to multiply the numerator and denominator by e to the negative 2x, right? So the numerator by e to the negative 2x. To maintain equality, I have to multiply by e to the negative 2x at the bottom. And this is multiplied by x on top and e to the 2x plus 1 at the bottom dx. So this is equals to the integral from 0 to infinity of x e to the negative 2x divided by multiplying this with this using the laws of indices. That is going to be 1 plus e to the negative 2x dx. And this is the same as the integral from 0 to infinity of x e to the negative 2x, and then multiplied by 1 all over 1 plus e to the negative 2x dx. Cool. So I am going to rewrite the denominator like this. So x e to the negative 2x, I am going to rewrite the denominator as 1 all over 1 minus negative e to the negative 2x like this, and then dx. Cool. Now let's compare this one to the geometric series, right? If we have 1 all over 1 minus x, the geometric series, this can be written like this: summation n from 0 to infinity of x to the n. So if I have 1 all over 1 minus negative e to the negative 2x, this using the geometric series, this is the same as n from 0 to infinity, the summation of negative e to the negative 2x. All this one raised to the power n. So this one can be simplified into the summation n from 0 to infinity of negative 1 raised to the power n e raised to the power negative 2nx. And this is the same as 1 all over 1 minus negative e to the negative 2x. So in place of this in the integral, I'm going to replace it with this. Cool. Now let's replace that in our integral. I is going to be the integral from 0 to infinity x e to the negative 2x, and then in place of that, that's going to be the summation n from 0 to infinity of negative 1 raised to the power n e raised to the power negative 2nx, and then dx. Cool beans. So I here is going to be equal to the integral from 0 to infinity is summation n from 0 to infinity of negative 1 raised to the power n, and then this, which is x e to the negative 2x multiplied by this, that is e to the negative 2nx dx. Now you can use laws of indices there. So this is going to be the summation. I'm switching the summation sign and the integral sign. Negative 1 raised to the power n, the integral from 0 to infinity of x. Using the laws of indices for this one, that is going to be e, summing the exponents. Negative 1 is common, pull that one out. Then you are going to have 2n plus 2, and then x common out, and then dx. So this is what we have after applying the laws of indices. Now let's do a substitution, right? I am going to let u to be equal to 2n plus 2 all times x, that is this one. So when I do that, then x is going to be equal to u all over 2n plus 2. So dx is going to be equal to 1 all over 2n plus 2 du. The change in limits: when x is equal to 0, the lower limit, u is going to be equal to 0 from here. And when x is equal to infinity, u is going to be equal to infinity as well. So the limits will not change, right? So now the integral in the u world is like this. This is the summation n from 0 to infinity, negative 1 raised to the power n. The integral from 0 to infinity, the limits will stay the same of x. X is the same as this guy, right? So that is u all over 2n plus 2. Cool. And then e to the, this one is u, so negative u. And dx is the same as 1 all over 2n plus 2. Du, that is dx here. Okay, so now let's simplify this integral. This is the summation n from 0 to infinity of negative 1 raised to the power n, and then the integral from 0 to infinity of u e to the negative u du all over this times this. That is going to be what? That is 2n plus 2 all squared. this has nothing to do with u, our variable. So we are going to bring it out of the integral sign. That is going to be the summation n from 0 to infinity of -1 raised to the power n divided by 2n plus 2 all squared. And this is the integral from 0 to infinity of u raised to the power 1 here. Permit me to write it as u raised to the power 2 minus 1, right? And e to the negative u du. And now I'm going to compare this one to the gamma function. So we have gamma of a number, let's say m. This is the same as m minus 1 factorial. And this can be written as the integral from 0 to infinity of x raised to the power m minus 1 e raised to the power negative x dx. This is the gamma of m. So if you are comparing this one to the gamma function, this one is just like the gamma of 2, right? So let's replace that in the integral. I is going to be the summation n from 0 to infinity of -1 raised to the power n all over. This one can be written as 2 is common, you can factorize it out. You have n plus 1, right? And all this one squared. And then this one is the gamma of 2. And gamma of 2 is what? 2 minus 1 factorial, which is 1 factorial. And 1 factorial is 1. So the integral just reduces to the summation n from 0 to infinity of -1 raised to the power n all over. This is 2 squared multiplied by n plus 1 squared. Alright, so I here is going to be equal to 2 squared is actually 4. So 1 over 4 is a constant under the summation. I can bring it out 1 over 4. Then I have the summation n from 0 to infinity of -1 raised to the power n all over n plus 1 all squared. So this is what our integral has been reduced into. So now we have to now find the summation of this. What is this one summing to, right? So that is the task now. So permit me to write a few terms of this summation, right? Just the first few terms. This is summing to infinity. So if you plug in 0, -1 raised to the power 0 is going to be 1, and the denominator is going to be 1 squared. So we have 1 over 1 squared. When you plug in 1, that is going to be a negative value. So it's going to be 1 all over. The denominator is now going to be 2 squared. When you plug in 2, that is going to be positive 1 all over 3 squared. When you plug in 3, that is going to be -1 all over 4 squared. This one continues until infinity. So the next term is going to be plus 1 all over 5 squared. And the next one is going to be minus 1 all over 6 squared. This actually continues until infinity because it's summing to infinity. Now let's group this one into even denominators and odd denominators, right? So this is 1/4 outside. Now let's put the odd denominators in one side. So we have 1 all over 1 squared. The next odd denominator is this one. That is going to be plus 1 all over 3 squared. The next is this. That is plus 1 all over 5 squared. And then this continues until infinity. Then you also have the even terms. The even denominators, that's 2 squared, 4 squared, and 6 squared. But all these ones are negative. So you have -1 all over 2 squared, minus 1 all over 4 squared, minus 1 all over 6 squared, like this. And this one continues until infinity. Okay, I is going to be equal to 1 over 4, and then this is 1 all over 1 squared, plus 1 all over 3 squared, plus 1 all over 5 squared, plus, and so on and so forth. And this is -1 is common here, so I'm going to factorize -1 out of this, and that is going to be 1 all over 2 squared, plus 1 all over 4 squared, plus 1 all over 6 squared, plus, and so on and so forth up till infinity. So now permit me to call this one the odd denominators A and the even denominators B, right? So I here is going to be equal to 1 over 4, and then the sum of these ones, permit me to call that one A, and the sum of this one, permit me to call that one B. So if you're able to find what the sum of these ones and these ones will be till infinity, then we can find the value of our integral. Okay, so before we know this, we have to know that the summation, if we have the summation n running from 1 to infinity of 1 all over n squared, this is the same as 1 all over 1 squared plus 1 all over 2 squared plus 1 all over 3 squared plus 1 all over 4 squared plus 1 all over 5 squared plus 1 all over 6 squared, and so on and so forth. And this is the Basel problem, which was solved by Euler, and this sums to pi squared over 6, right? So this one sums to pi squared over 6, but this pi squared over 6, you can write it as the sum of the odd terms and the even terms. Those are the denominators. So if you have 1 all over 1 squared plus 1 all over 3 squared plus 1 all over 5 squares, these are the odd denominators, right? Plus and so on and so forth. Then you also have the even denominators, that is 1 all over 2 squared plus 1 all over 4 squared plus 1 all over 6 squared. This one continues until infinity, and this one sums to pi squared over 6, right? So we see that these are the odd denominators and these are the even denominators. So this is A initially, this is A and this is B, right? So that means that A plus B will sum to pi squared over 6, correct? Now let's find what B will sum to, right? So B here is the even denominators, so let's look at that again. So B is going to be equal to 1 all over 2 squared plus 1 all over 4 squared plus 1 all over 6 squared, and so on and so forth. So B is going to be equal to 1 all over 2 squared plus 1 all over 4 can be written as 2 times 2 squared plus 1 all over 6 can be written as 2 times 3 squared, plus and so on and so forth. Okay, so B is going to be equal to 1 all over 2 squared plus this one, using the laws of indices, is 1 all over 2 squared times 2 squared, 1 all over 2 squared times 3 squared, and so on and so forth. Okay, B is going to be equal to, we see that 1 all over 2 squared is common for all the terms, right? So I have to factorize 1 all over 2 squared out. What is left here can be written as 1 all over 1 squared plus this here is 1 all over 2 squared. This one is left with 1 all over 3 squared, and this one continues until infinity. But what is this sum, right? That sum, 1 all over 1 squared plus 1 all over 2 squared plus 1 over 3 squared, that is the same as the Basel problem, which is pi squared over 6. So this one is pi squared over 6. So B is going to be equal to 1 all over 2 squared is 4, and then times the sum of this is pi squared over 6. And this one is equals to pi squared over 24. Correct. So we have gotten the summation of B. So the even denominators will sum to pi squared over 24. Now that we have B to be pi squared over 24, we can find the sum of A, right? Because we know that A plus B will sum to pi squared over 6. So we have A plus B. B is summing to pi squared over 24. So that is A plus B, and B is pi squared over 24, which is equals to pi squared over 6. So A is going to be equal to pi squared over 6 minus pi squared over 24. And therefore A is going to be equal to, we can multiply by 4 on top here, 4 pi squared all over 4 times 6 is 24 minus pi squared over 24, and that is equal to 3 pi squared over 24. Therefore A sums to 3 pi squared over 24. Now that we have A and B, what they are summing to, we can now wrap up our integral. So our integral I, if you can recall, is equals to 1 over 4 into A minus B, correct? So when we go up here, so our integral I is 1 over 4 multiplied by A minus B. We have found the sum of A and B, so we just plug them in and wrap up the video. As simple as that. So A is 3 pi squared over 24. So that is 3 pi squared over 24, and B is pi squared over 24 from here. So this one is equals to 1 all over 4, And then 3 pi squared minus pi squared is 2 pi squared all over 24. And this is the same as 1 over 4 times pi squared over 12. And this is equals to pi squared over 48. And therefore I here is going to be equal to pi squared over 48. And this one agrees with the answer that MIT gave for this beautiful integral. So we see that this integral is very simple, but it entails. So the answer to this beautiful integral is pi squared over 48. And this is the trick that I wanted to show you. So if you enjoyed the video, please give me a thumbs up and subscribe to Calculus Diaries for more content. And then I'll see you in the next one. Bye bye.